Howdy y'all, I hope you had a fantastic Labor Day weekend and subsequent week. Today we're going to be talking about plate tectonics, which is a topic near and dear to my heart as a structural geologist. This is what I study here at CSUN, and I find it very interesting, and I hope you do too. Now, you're probably familiar with one way we divide Earth's interior into the crust, the mantle, and the core. We know most about the crust because it's what we experience on a day-to-day basis. We walk on it. It's the outermost, thinnest layer on Earth. Below that is the mantle, which we don't know as much about because obviously it's underneath the crust and we've never been there, but we do know the results of what the mantle does by studying what happens in the crust. It's the thickest layer in the Earth's interior, and it's very important when we consider plate tectonics. The innermost layer, of course, is the core. That's the densest material in Earth, and we don't know very much about it because, again, we haven't even been to the mantle. How would we get to the core? There's another way we can divide Earth's interior. We can divide it into the lithosphere and the asthenosphere. Now, the lithosphere is the crust and the uppermost part of the mantle. The asthenosphere is right below the lithosphere. A lot of people compare Earth's surface to the surface of an egg, where you have that thin shell and then the interior is sort of that egg white and egg yolk. This is a very good analogy. However, Earth's surface is like an egg but with the shell cracked, with 12 major plates covering the surface of the egg or the Earth. These lithospheric plates move independently of one another because of convection currents within the mantle. As these plates move, they collide with one another, they divert from one another, and they slide past one another, and that creates a lot of the landforms we see in our world today. Now, plate boundaries can interact in three main ways. You can have a convergent boundary, a divergent boundary, and a transform boundary. In a convergent plate boundary, two plates are colliding with one another. Now, the exact nature of this collision is going to be dependent on what exact materials make up each plate. If one is more dense than the other, it will slide underneath the less dense plate and create what's called a subduction zone, which creates volcanic arcs, island arcs, mountain chains. It does a lot of cool things on Earth's surface and in Earth's interior. Plates can also divert away from one another. Now, when this happens, when two plates go away from each other, a void is created in between these two plates. And in that void, magma from underneath the Earth's surface will well up and start creating a large mountain chain. That's what's currently going on in the Atlantic Ocean. We actually have a mountain chain, which we call the mid-ocean ridge, that splits the Atlantic Ocean almost in two. And that is the exact location of where the two plates are diverting from one another. And a transform boundary is just where plates slide against one another. For example, here in Los Angeles, we're by two plate margins, which are the boundaries of those plates, that are slowly sliding past each other and causing earthquakes as they do. Up in Washington and Oregon, instead of the plates sliding past each other, they're colliding with one another and creating large mountain chains and volcanic arcs along with them. Now, one very important concept when it comes to tectonic theory and how these plate boundaries change the Earth's surface is how it creates and destroys lithosphere. As you can imagine, if two plates are converging with one another, one is more dense, so it creates a subduction zone. That arm of the subduction zone is going straight into the asthenosphere, where it's being destroyed by the heat and pressure in the Earth's interior. In divergent plate boundaries, as those two plates are going away from one another, magma is filling that void and creating both the mid-ocean ridges and new lithosphere. So at the same time, simultaneously on Earth's surface, we are both destroying and creating new lithosphere. That's why the oceans are only generally 250 million years old. That's relatively young geologically speaking, and it's because the rock is constantly being recycled in this lithosphere cycle of destroying in subduction zones and creating in divergent plate boundaries. Now, transform plate boundaries don't create or destroy any sort of lithosphere. It's just two plates sliding past each other. Now, I talked about Los Angeles because we have a transform boundary between the Pacific plate and the North American plate. Now, that fault system is responsible for the mountains that we see here in the Los Angeles area, and it's also responsible for the basins we have. This is very typical of tectonically active areas where mountains are currently being built as we speak. they might be being built only in millimeters or centimeters per year. But when you start looking at a geologic timescale in millions of years, that's quite fast. And so the mountains here are going to continue to grow in the future. Over on the East Coast, we don't have any active tectonic plate boundaries. The boundary on the East Coast is far out into the Atlantic in those mid-ocean ridges. So the East Coast of the United States is relatively quiet compared to the West Coast of the United States because we don't have the same plate boundaries dictating how things are developing. One really cool thing about plate tectonic theory is the idea of continental drift, that when you start looking at these continents over millions or billions of years, you can see how the lithosphere that makes up the continents moves and changes and creates supercontinents, which then break up and create individual continents, which then reform again and then break up and reform, and it's a constant cycle. A lot of people are aware of the last supercontinent that occurred. It was called Pangaea about 250 million years ago. That was only the last supercontinent. There have been 7 times when all of the continents mashed together and formed a supercontinent and then broke up. We're currently part of the cycle where the last supercontinent broke up and it's slowly reforming again. So in a couple 100 million years, we're going to see another supercontinent, and everything else would just be ocean. How cool is that? So one question is, how do we know plate tectonics exist? Well, today it's sort of an easy answer. We have lots and lots of seismic recording stations that can record the exact movement of the plates year by year by year. Back in the 1800s and 1900s, though, it was a little bit more difficult to ascertain. One of the key factors that helped us in our understanding of how continents move was through fossils. A lot of researchers would find tropical fern fossils in Antarctica, Australia, Africa, and South America. All of these places are not connected very well, and also not all of these places are in the tropics. So how did those fern fossils get there? Well, some time ago, I think 170 million years ago, could be wrong on that, all of those continents were formed together in Gondwana, which was a supercontinent, and they were located at the equator where tropical ferns would grow. Since then, they have split apart, and so what you end up having is the same fossil in different land masses across the world. As we learned more and more about this phenomenon, we started to map the ocean floor, and we noticed how mid-ocean ridges were forming, and we were able to basically take the mid-ocean ridges and sort of turn back time and imagine, okay, so it's forming from a divergent plate boundary. What if we push the plates back in and reverse time? And so you quickly notice that Africa and South America squish back together if you roll back time. Another way that we knew about plate tectonics before these sensitive instruments was through how we mapped earthquakes and volcanoes. Now, if you pull up 3 maps, a map of all the earthquakes in the world, a map of all the volcanoes in the world, and a map of plate tectonics and current plate boundaries, you're going to notice they're very, very similar. That's because most volcanoes and most earthquakes are created by plate tectonics and are created on plate margin boundaries. The phenomenon is so obvious. If you look at the Pacific plate that goes around the Pacific Ocean, you'll notice it almost looks like just a ring of earthquakes and volcanoes. We call that the Ring of Fire in the geoscience community because it quite literally is a ring where the Earth is extremely volatile and has lots of volcanoes and earthquakes. I completely forgot to film an outro, so please enjoy this picture of my cat. I hope the video was helpful for you, and I hope you have a fantastic week. If you have any issues or questions, please do not hesitate to reach out to me by email, and I'd be happy to figure things out with you. Thanks for your time, and have a great day.